I want to compare and contrast RL and RC circuits. So imagine you have a network of resistors and you collapse it into a single equivalent resistance. Also, you have a network of inductors and you collapse them, and similarly for capacitors, and reduce down into either an RL or an RC circuit depending upon the type of energy storage element that you have. And then let's analyze these and have a look at the similarities in the way that they respond. So looking at the inductor circuit, the RL circuit, I can apply KVL around that loop, and I will get that the voltage plus IR is equal to 0. And then I can substitute in what I know about inductor dynamics and replace that voltage with L di dt plus IR is equal to 0. And then I can rearrange, put all the coefficients together, and I'm going to write them in this form. So L divided by R times di dt plus I is equal to 0. And that's the differential equation that describes a RL circuit. Let's go and have a look at the similar situation for the RC circuit. So again, using KVL, I will arrive at this expression. So V plus IR is equal to 0. Then I can sub in what I know about capacitor dynamics, and that will give me V plus C to V dt times R is equal to 0, and I can clean that up and kind of put it in the same order as the equation on the left. I will have R times C times dV dt plus V is equal to 0. And we have a similar pattern to before, and that will be the differential equation that describes the RC circuit. So what can we notice about these equations? Well, firstly, for RL circuits, it's the current is the predominant variable that we're going to solve for, and for RC circuits, it's voltage. Another thing that we can notice is if we look carefully at the coefficients that we have at the front of the differential term, we can learn something interesting about the units of these parameters. So if you consider an equation like this one, where we have a term V, which we know is measured in volts, and we add something to it, then for that to be dimensionally consistent, we would require that both of those terms have the same units. So basically this portion here must have units of volts in order for this equation to make sense. And if that has units of volts, well, we can analyze what each of those parts within. So for example, we have dV here, so differential element dV, that has units of volts. So in case you're not familiar with that, the differential element has the same units as the actual variable itself. So dV has units of volts, which means that dV dt has units of volts per second. And so the only way that we wind up with RC dV dt having units of volts is if RC has units of seconds. And so this is quite an interesting statement. We're saying here that resistance times capacitance has units of seconds. And in fact, this is a true statement. This is actually the so-called time constant of our system. So the parameter here, RC, is called the time constant. It's called the time constant of the circuit. So just the value of the total resistance, or the equivalent resistance, and the value of the equivalent capacitance multiplied together gives us this time constant. Now we can apply a similar argument to the inductor equation, and where we're going to end up with that is that L over R has units of seconds. So again, L over R is the time constant for this circuit. And so it will describe basically how quickly this system responds. We can write down the solution to these differential equations. We've solved them a couple of times already in different videos. I'll basically go straight to the solutions. So the solution for the RL circuit is the following, that we have I of t is equal to some initial current times an exponential negative t divided by this parameter tau, where tau is our time constant, is L over R. The solution for the RC circuit is quite similar. It's just expressed in terms of voltage. So it'll be an initial voltage times e to the minus t divided by tau, where tau, our time constant, is just R times C. So in both cases we have quite similar dynamics, and it's worth just reflecting and understanding a little bit about the shape of this sort of decay. So as an example, if I take the RC circuit, then I can plot voltage versus time, and we have some initial voltage V0, and then we have this exponential decay that actually runs kind of ahead over time. And so the time constant sort of defines the scale at which this this decay actually happens. And so we can kind of ask ourselves the question of, how much has it decayed after one time constant has elapsed? And so let's ask, so what happens to V of t after one time constant worth of time has elapsed. In other words, when t is equal to tau is equal to R times C. So we can kind of substitute into our equation. So it was V of t is equal to V0 times e to the minus t over tau. But we're saying substitute t equals tau, which is going to give us V of t is V0 e to the power minus 1, because the fractions there will cancel. So e to the power of minus 1 is actually 0.3678 times V0, so like about 37% of the initial value. So we can kind of imagine here on our diagram that this time constant is about kind of that far through into the decay. And you can solve for 2 time constants or 3 or so on to see how much of a decay you actually get. But as far as kind of estimating the speed at which this circuit will respond, this gives you a kind of a rough ballpark figure that you can use in estimating. So the time constants for the inductive circuit is L over R. The time constant for the capacitive circuit is R times C. And you should know those, and you should sort of recognize those time parameters and kind of understand the meaning in terms of the exponential decay of the parameter.